All right, let's go ahead and get started. So normally I have notes for you, right? And it's well, I've been trying to stay pretty organized. This particular section, I didn't want to make the notes because I don't know how it's going to go. All right. So what I wanted to do is just kind of wing it, and that way next semester I'll know what to do for my notes. All right. You're the guinea pigs. All right, good. So we're going to be doing 5, 6 today. Not yet. Hang tight. Well, you may have one today. Yeah. As far as the review for the exam, I have it prepared. I don't have it printed, and the reason why is because, again, I didn't know how today was going to go. So there's some stuff on that review that I may or may not get to, and I didn't want to give you something that had stuff on it that we may not cover. So what I'm going to do is I'm going to put it in Canvas tomorrow, all right? And I will also email it to you. So it'll be in Canvas under Files. It'll also be in your emails. Okay, I need everyone's attention. I know everyone's excited to see each other, but I need your attention for this, all right? Guys? Yes? Ready? Okay. We are going to talk about what are called complex zeros. And I'm always a little on the fence about this because it's very difficult to study complex numbers. I'm going to try and explain why, and then we'll get to what you're going to need to know for the test. So first of all, what is a complex number? I'm not asking you. We're just thinking about this. Complex numbers. Well, what we're familiar with is the number line, right? All the numbers that you could ever think of that live on this number line are what we call the real numbers. So you have the real numbers here. So everything you can think of, right? 1, 2, 3, 4, all the fractions you can think of, those weird numbers that they call the irrational numbers like pi, e, right? They all live on this number line somewhere. But it turns out that there is another group of numbers called the complex numbers that involve what's called the imaginary unit, this I thing. We've heard about it. I'm sure you've heard about I. But what it's going to wind up doing is it's going to change our view on these numbers. These numbers are actually going to live in a bigger set of numbers. So I'm going to start by defining what the imaginary unit is. So the imaginary unit is what it's called, is I. And by definition, it is the square root of -1. It is what you get when you try and take the square root of a -1. Traditionally, we would have said this is impossible because it's impossible to square a real number and get a negative answer. So like when we say over here, like square root of 4, we say that was 2. Why? Because when you square 2, you get 4, right? If we say square root of 9, we've all been happy to say 3. Why? Because when you take 3 and you square it, you get that 9. So what we're saying here is that if the square root of -1 is I, that means when I square I get what? -1. So this means, by the definition here, that if I square both sides of this, I get -1. And that is the property of I. And I believe I've talked earlier this semester about how, imaginary numbers got kind of a bad rap because, people didn't believe they existed. All right, so that's what I squared is. What would I cubed be? Careful. Do you agree that that would be I squared times I? Because don't you add the exponents up? Isn't that I squared times I, which would be I cubed? So it would be I squared, which we just said was what, -1? Times I, right? So we just write -I. Now you could say negative square root of -1, but we're just going to say it's -I. And then what would I to the 4th power be? Look at that as being I squared times I squared. Do you agree with that? I to the 4th is I squared times I squared. What's I squared? -1. So that's -1 times -1, which is 1. All right, so let's go back and just think through this again. What we're saying is that I to the 1st power, right? I to the 1st power is just I, which we know by definition is square root of -1. I squared is -1. I cubed is -I. I to the 4th is 1. What would I to the 5th be? Well, isn't that I to the 4th times I? But what was I to the 4th? 1. What's 1 times I? Just I, right? Just I. Then what would I to the 6th be? Now it's going to start repeating itself, right? I to the 6th would be, you could say I to the 4th times I squared. What was I to the 4th? 1. What's I squared? -1. So this is -1. And yes, there's a pattern here. I to the 1st power is the same as I to the 5th power. I squared is the same as I to the 6th. I cubed would be the same as I to the what? 7th. I to the 4th would be the same as I to the 8th. And then what would happen? It would start repeating again. So what's the repetition that we have? What is the repeating pattern? We start with I, then the next thing that happens is -I, then the next thing that happens, -1, then the next thing that happens is -I, and then the next thing that happens is 1. And then it just keeps doing that, right? Depending on the power. So I raised to any power is one of these 4 answers, isn't it? Okay. Does that make sense to everyone? Okay. That's just some properties of I. Now, this is what we call the imaginary unit. Now let's talk about what is a complex number, right? Because I set up here, complex numbers is what we're focusing on. We know what the real numbers are. In order to talk about complex numbers, we have to first define this thing called the imaginary unit. And now let's define complex numbers. So for a complex number, are written as follows. A plus BI, where A and B are real numbers. This right here, the A, is called the real part of the imaginary number. This B is called the imaginary part. The reason it's called the imaginary part is because it's the part of the number that is attached to the imaginary unit. This is multiplication between these two, B times I. All complex numbers have this format, right? This right here is just a number off the number line. This right here is a number off the number line, but you attach an I to it. Okay, now let's just see if you can make sense out of this. Let me give you some examples here. You tell me, yes or no, is this a complex number? 3 minus 2i. Is that a complex number? According to the way I've defined complex numbers, is that a complex number? Yes, that's a complex number. It has, what, 3, which is like the a. It has a number in front of I. In this case, what would our b be? What would our b be? -2, because that's a negative sign, right? So you could rewrite this as 3 plus -2i, right? Something like that. Okay, so tell me, what's the real part of this complex number? What's the real part? 3? So the real part is 3. And what's the imaginary part? Just the -2. Okay, you don't include the I. You're just saying that's the part that's attached to the I. The imaginary part is the -2. Why are you looking like that?
Okay, that's not what's open.
No, it's just the B. Okay. As opposed to, oh, well, what I'm trying to show you here is that this is A plus BI, right? All subtraction can be written as addition of the negative. So this does follow the format of A plus BI. With me? Okay, let me show you another one. You tell me if this is a complex number or not. Is that a complex number? Let's take a vote. So yes, it is a complex number, or no, it is not. All right, so the answer is yes, it is a complex number, and here's why. I can rewrite that as 0 plus -7i, can't I? In which case, what's A? What's the real part of this one? The real part's 0? And then what's the imaginary part? -7. That makes sense? Yes.
What if we did -3 minus 7i? That would still be.
Yes. -3 minus 7i. If you had that, -3 minus 7i, that would be a complex number. Your A here, I'm just going to put A and B. Your A here, which is the real part, would be what? -3, and then your B here would be what? -7. So it satisfies being a complex number, yes. Well, let me do a couple more examples. All right? Can I keep going? Okay, how about this one? Is that a complex number? So let's vote. We'll vote yes or no for this. Is this a complex number? Yes or no? Everyone done voting? It is a complex number. Okay? It is 5 plus what? 0i. All right? Where A is 5 and B is 0, right? Now look, this is pretty profound, all right? It was, but it's more to make this point. That really means that every real number is a complex number. But every complex number is not a real number. Look at this right here. This is not a real number. All of it together is not a real number because it has that imaginary piece to it, right? So it can't be on our number line. But if you take a number on the number line, it actually does satisfy being a complex number. So what we can do is give a visual of what's happening. If you were to throw all the real numbers into a pot, there they are. They live in this pot, right? Well, it turns out that every one of those lives in a bigger pot of numbers, which are your complex numbers. So look, the real numbers are inside the complex numbers, right? Which means that the number 5 is a real number. Yes, it is a real number, but it's also a complex number. You have complex numbers like 3 plus 2i that are complex numbers but are not real numbers. It's kind of like you are students in this class, right? You are also students at Northwest Vista. That's what we're saying. Number 5 lives in this class, but number 5 lives in Northwest Vista too. But there are students that are in Northwest Vista that are not in this class. That's what the complex numbers are, if that makes sense. And so that kind of blows the doors off of everything that we've known about numbers. So what we want to do now is we want to have some way of visualizing where these numbers are. Like the number 5, if I say, hey, show me visually where 5 is, everyone would draw a number line, put 0, and then put 5 to the side, wouldn't you? But how would you put 3 plus 2i? Where do you put it? So let me show you how we do it. Visualizing complex numbers. So what we do is we draw our real number line. Okay? That's the real number line. So I'm going to call it the real axis. It's the real axis. And then I'm going to come in with something that we have never done before. I'm actually going to make this two-dimensional. Now, we have done this when we're graphing, right? We have the XY plane. The real number line has always been just a line. Now, for the complex numbers, we're going to add a second dimension to the line to make it a flat sheet of paper instead of a single straight line. And this axis up here we call the imaginary axis. Now, let's put some numbers down. So let's start with the number we're comfortable with, like 5. This point right here that I just put is a real number, yes, but we also said it was a complex number. And I told you it was 5 plus 0i, right? Okay. How would I plot this one? I want you to think about it. 3 plus 2i. Well, what's the real part? 3. So that means my real part should be 1, 2, 3. But then what's the imaginary part? 2. So what? Maybe I should just go up 2. Right? So 1, 2, up. Put a dot here. That is your complex number 3 plus 2i. So what I'm trying to get you to see is that to visualize a real number, you just need a single number line, don't you? To visualize a complex number, you need 2 dimensions. You need 1 dimension for your left and right. You need 1 dimension for your up and down. Or you need 1 dimension for your real part, 1 dimension for your imaginary part. Okay, help me with this one. I want you to help me put 2i on this graph. Where's 2i? 0 up 2. That's it. So your real part's 0, isn't it? And you go up 2. So it'd be right there. See that? Yeah, it's the number in front of I tells you which way to go up and down. Okay? That's how we visualize it. Now, the reason why I said, and we're going to wing it today, is because most of the research and stuff that I did in grad school was based in complex numbers. So I'm like very passionate about this stuff. It's hard for me to not get distracted and start taking you off in places that we don't even need to go. All right? So with that said, I just want to point out that there's something happening here in the complex numbers that that doesn't happen in the real numbers. I mean, there's a lot of things, but one of the most basic fundamental properties of real numbers we do not get when we have complex numbers. So I want to point it out to you. If I give you two real numbers, okay, let me give you, or someone give me a real number. 3 and, I heard 5, okay, 3 and 5. If somebody gives you two real numbers, there are three possible conditions or relationships we can have with these numbers. We can either have that this is true, or this is true. Do you agree? They're either, one of them is either bigger than the other, one of them is less than the other, or they're the same number. This is called trichotomy. Tri meaning three. Three possible relationships. Okay? So on what we're saying is if you look at the real number line, if you're talking about real numbers on the number line, we're basically saying that any two numbers, one of them is either to the left of the other, or to the right of the other, or they're the same number, right? Do you see the issue you would have with complex numbers? Yeah, how do you define what's bigger and smaller? Do y'all understand what I'm saying? Like, which number is bigger, this one or this one? Well, they have the same imaginary part, don't they? The real part of this one's bigger than the real part of this one. So does that mean it's bigger? How do we define it? Or like number 5, right? Is this number bigger than this number? Again, there is no such thing as trichotomy in the complex numbers. So we lose those three possibilities, we lose them completely, which changes everything. The whole structure of the number system completely gets kind of twisted around. So it's a dangerous place to play in the complex numbers. Just want to point that out. Do you remember me using this notation for the real numbers? Double struck R? All real numbers, right? That just means the real number line, okay? This two-dimensional picture, the complex numbers, we use a double struck capital C. This means the complex numbers. So that means everything in here. All right, so I think hopefully we have a basic idea of what a complex number is, what it looks like visually. Now I would like to just do a couple of things that we did when we first were learning numbers in grade school. We learned how to add them, subtract them, multiply, and divide them, didn't we? So I just want to make sure we know how to add, subtract, multiply, and divide complex numbers real quick. So let's start with this. Basic arithmetic with complex numbers. And the best way to do this is with examples. So let's do some addition. So here's an example. I would like for you to take 4 minus 3i. I'd like for you to add that to 3 minus 2i. So do you see that I have two complex numbers here? I have one complex number here, one complex number here. I'm adding them together. Well, just like before, we ignore parentheses unless we have to distribute things through. So I'm going to just remove all parentheses. And then after that, let's collect what we would consider to be like terms. So let's collect real parts and imaginary parts. I have a 4 and a plus 3, right? Which gives me a 7. And then I have a negative 3i, and I take away 2i. Just treat that like negative 3x minus 2x would give you negative 5x. So negative 5i, and we're done. Notice that our answer is a complex number. So we start with two complex numbers, we add them together, we get a complex number. How about subtraction? Same thing, except we'll have to take care of that negative sign, right? So let's do the same two numbers. time subtracting. So I will drop the parentheses on the first one, no issues. To drop the parentheses on the second one, I have to pass a negative through, which changes the signs. And now I combine them. So what would my result be here? 1 minus 1i, which can I just put I? All right. 1 minus I. Pretty easy, right? Nothing fancy here. Okay, let's try multiplication. Let me start with this one. We'll go and do something like the one before in a second, but let's do this. How about 3i? Is that a complex number by itself? Yes? What's the real part of this complex number? 0, okay? And if I want to take that and I want to multiply it times 7i, which again is another complex number, then how would I multiply those? Not distribute, but you just rearrange and just do like the 3 times the 7, which is 21. And then you do the I times the I, which is I squared. But what's I squared? -1. So this is really -21. Let me go a little slower. 21 times -1, which is -21. Well, okay, you mean complex numbers. These two are complex numbers, right? Our answer is a complex number, but it's actually a real number because it's just -21. Remember,
all numbers are complex numbers, but not all.
That's right, but not all
Real numbers are complex numbers, but not all complex.
Are real numbers, yes. These two are complex numbers that do not live on the real number line, right? These two do not live on the real number line. But when you multiply them together, their answer lives on the real number line. It's kind of interesting. Right? Where would 3i and 7i be on the number line? Where's 3i? That's 3i, right? Where's 7i? Right there, right? If you multiply those two numbers together, your answer is right here. It's weird. There's so many like awesome properties of complex numbers, I can't even begin to explain it. I mean, it's really a cool thing that's happening here. And see, I can't avoid it. I'm going to have to. What's the length? If I measure the length from here to here, what's that length? What's the length from here to here? Okay, 3 times 7 is what? 21. So I know that the length from the answer I get, I know the length, the distance from it to the origin is 21. But why do I know it's here? Well, let me show you. What's the angle that gets you to this number? What's this angle? 90 degrees. What's the angle that gets you to that number? 90 degrees. What's 90 plus 90? 180. That's why we go all the way. I mean, there's so many like underlying subtle things that we could get into, but we're not going to. All right? It's beautiful stuff, man. It's really beautiful stuff. All right, let me do another multiplication. How about this one? 3 plus 2i times -3 minus 4i. All right, now I've given you two complex numbers. They both have real parts, right? 3, and this one has -3. I want to multiply. What do you think you do?
Foil.
Like FOIL. Yep. So we're going to go 3 times -3, which is -9. 3 times -4i. -12i. 2i times -3. -6i. And this one's the one you got to be kind of careful with. 2i times -4i. -8i squared. But I squared is going to turn into a -1, right? So let's put this together. This is going to be negative 9 minus 18i. I'm putting the two middle ones together. And then that last one is negative 8, and then I squared became negative 1. Negative 8 times negative 1 is positive 8. And then I'm going in a lot of detail here. Negative 9 minus 18i plus 8, which gives you negative 1 minus 18i.
Very interesting.
Yeah. What's good about this is that, you know, it follows all the things that we normally would see with numbers. If you add, subtract, multiply, divide numbers, your answer are the answer you get are numbers. Here, when you take complex numbers and do the same thing, your answers are complex numbers. Now, negative 21 is a complex number. It's just also a real number. So, all right, that's basic arithmetic. I'm not going to do division. All right, division's a little bit more involved, and we don't need it for today. All right, so this is just to get you acquainted with some of the operations. Okay, now, why in the hell is this important? All right, so let's now talk about solving some equations. I want us to solve this. X squared plus 9 equals 0. So if you were to try and solve that, maybe you would be thinking on the left side to do some factoring, right? But you can't factor, it's not like a difference of squares. So maybe you think, all right, hey, we had that rational zero test, remember synthetic division thing? Maybe that would work. Maybe. Let me see. What would happen if I try synthetic division? What would my list of numbers be? I'd have 1, 3, and 9, right? I'm looking at all the factors of 9, and that would be my list. What would go in the synthetic division box? 1, 0, and 9, right? And what would go on the outside? Well, we start this list, right? So let's try 1, see if it works. 1 comes down, 1, 1, 1 comes down, 1, 1, 1, doesn't work, right? So you try negative 1 now. 1, negative 1, negative 1, 1. That doesn't work, right? So then you move on to 3. 1 comes down, 3, 3. 9, oh, not negative 9 though, right? Y'all following me? Okay, so that doesn't work. Let me change this to a negative 3. Does that help? 1 comes down, negative 3 comes down. Negative 3 times negative 3, 9, doesn't work. 9, try 9 out here. 1, 9, 9 comes down, no go. Negative 9 is not going to work either. So we are stuck, basically, right? I said that this thing works if your zeros are rational numbers. And I said nothing about complex numbers because we didn't even know they existed, right? So this will work if your answers are rational, real numbers. It's gonna not work as good for us if these are imaginary numbers or complex numbers as answers. So let's try this. Move the 9 to the other side, make it a negative 9. Take the square root on both sides. Whenever you take the square root on both sides of an equation, you must do what? Plus or minus. You have to do that when you come in and take square root. What's the square root of negative 9? So let's talk about that. Before today, we would say no go, right? But now we want to really investigate what is the square root of negative 9. So I'm going to write this as this. Do you agree that that's 9 times negative 1? And then do you agree that that's the same as the square root of 9 times the square root of negative 1? Because we have a property of roots that if you have multiplication underneath, you can split it into 2 separate roots. What's the square root of 9? 3. And what's the square root of negative 1? I. So your answer is 3i for this, right? So that means that x over here has to be plus or minus 3i. That means we have 2 solutions, don't we? The 2 solutions are 3i and negative 3i. Let me check to see if they're correct. Let me start with 3i. If I plug 3i in here to the original problem, is this true? Let's see. I plug 3i in, and I square it, plus 9. Does that equal 0? Do y'all see what I'm doing? I'm plugging in one of these answers. I'll have to check negative 3i in a second. Okay, so let's square 3i. So what's 3i times 3i? So, or you could just square the 3 first, 9. What's I times I is I squared? Then plus 9. That's going to work because what's I squared? Negative 1. So that's going to turn this into a 9 times negative 1 plus 9. Does that equal 0? Negative 9 plus 9 is 0. That works. So that was a solution. Do y'all see that? Now, I'm not going to check negative 3i, but it would work also. Okay. Now, let me see if you remember this. Just do this on the side real quick. Recall that if I had, let's say I had factored something like this. What would you tell me, make the second one a plus. What would you tell me the solutions to this would be? X is 2 and negative 3, the opposite of what's in here, right? You said each of these equal to 0? These would be our solutions, wouldn't they? And we had said before that if you have we call them the x-intercepts, that you could use the x-intercepts to go back up and create the factors, couldn't you? So like if I told you that you had x-intercepts of 2 and negative 3, you could create the 2 factors x minus 2 and x plus 3, yes? That means that I should be able to take this original problem. I'm going to go to a new page. I should be able to take this original problem, and I should be able to factor it. And what it should be is x, x, and then my 2 answers, right? But change the signs. So my first answer was negative 3i. So positive 3i, so I put negative 3i here. And the other one was negative 3i, so I changed it to positive 3i. Does that make sense at all? I'm using the 2 answers we just got in the previous page, the 2 answers we had, to go back and create the factors of this quadratic. So just like we used these, we went backwards with them. That's what I'm doing here. So essentially what I'm trying to show you is that I have factored something that before was unfactorable. Right? All right. How about this? Solve x squared minus x plus 8 equals 0. Can you factor this right now? No, you can't break that up. So what have I told you in the past we use whenever we can't factor this? Quadratic formula. So let's go to the quadratic formula right now. I know that my solutions will be negative b plus or minus the square root b squared minus 4ac all divided by 2a. So what is negative b for us in this problem? The opposite of negative 1 right here. So 1 plus or minus square root. What's b squared? 1 minus 4 times a. What's a? 1 times c. What's c? 8 all over 2. But this is 1 plus or minus the square root of what? Yeah, this right here is going to give you a 32. So 1 minus 32 is negative 31 all over 2. And in the past, at this point, we would say, forget it, right? Because we have a square root of a negative number. But we don't, that doesn't trouble us as much anymore because we have the I. So let me rewrite that as 1 plus or minus the square root of 31 times the square root of negative 1 over 2. See if you agree with that. Is that the same? And what's the square root of negative 1? It's just I. So this becomes 1 plus or minus the square root of 31 I over 2. And I'm going to go one more step. This is equal to 1/2 plus or minus root 31 over 2I. Tell me what I did there. Just split it into two fractions, right? I did the 1 divided by the 2, which is this, then plus or minus right here. Then I did the root 31 over 2, which is this, and I just tacked the I onto the side of this. Do y'all see that? What is this right here? Is that a real number or a complex number? It's a complex number. What's the real part of the complex number? What's the imaginary part? It's both of these, because there's two answers here, right? But it's the root 31 over 2. That root 31 over 2 is a real number. But that's the imaginary part of this complex number. So our answer, we have two complex numbers as our answer, right? That means if we wanted to factor the original, right, the original problem, what I would do is this. I would take this. I would say that that's equal to, well, I'm going to need bigger space here. This right here would be equal to two things. Remember, we're going to use the opposite of what we see there. It's x, x, and then whatever our answer is here, right? Plus and minus of that. So what would happen if I change this to the opposite of everything I see? I would get what? Negative 1/2? And then this plus would change to a what? The one on top would change to a negative, and then root 31 over 2I. And then over here, I'm going to do the opposite of the bottom one. So what's the opposite of 1/2? Negative 1/2, right? But then what's the opposite of negative? Would be plus. I think I lost a lot of you right there. You could. That's what I was going to do when I said I lost a lot of you. Look, this is two answers. It's 1/2 plus root 31 over 2I. The other one is 1/2 minus root 31 over 2I. Agreed? Those are our two answers here. When you have two answers, to come back and create the factored form, you take the opposite in sign of what you see here. I'm referring back to this. We took, if our answer was 2, we went back and put negative 2, right? If our answer was negative 3, we went back and put positive 3. Here, we're doing the same thing. If my answer is this, I'm going to put x and I'm going to put minus this. What happens if I minus this? Negative here, negative here. That's this. If my answer is this, I'm going to do the opposite of this one here. So minus this, minus minus would become plus. I hope that helped. Yeah. Well, where did we get the x here? Remember, we're saying that if you start with this, if somebody gives you the solutions to an equation, those solutions, you can go backwards and create the factors. That's what we're doing. We're starting with the solution and going back to the factors. I try to show you by starting with it factored, we go from the factored form down to the solutions. But how do you go backwards? From this, you create what? X in a parentheses, and then... Mm-hmm. Parentheses. Two factors. Yes. Okay. Where? Right here?
Yeah, would you go x times negative 1/2 minus 31 down there?
Okay, that's what you want in parentheses, right?
Down there.
And then let's put them in parentheses in here. Okay.
Yeah.
So I'm putting in parentheses right here. It was a plus on that one. I'm going to put the parentheses on this one. It was a minus on this one. Yes? So yes, but what sign goes here?
Oh, then you got plus and minus.
It's the opposite. Look. Okay, I'm losing everyone. All right, look. Let's go back to this. Let's say that I have a polynomial function that's factored.
Okay, we're going trinomial here.
Let's say I have that, right? What are the x-intercepts of this? X is 5, x is 3, x is negative 1, right? Okay. Now let's act like I didn't give you this up here, and I said these are the x-intercepts of a polynomial. Create the factors. What you would do is you would do a parenthesis, and you would go and you would put an x, and then you wouldn't put 5, you would put what? The opposite. You would put negative 5. You would put another parenthesis, x, you wouldn't put 3, you would put negative 3. You wouldn't, here, another x, you wouldn't put negative 1, you would put positive 1, the opposite, right? That's what I'm doing here. These are my answers. These two things are like the 5 and the 3. And I'm going backwards now, and I'm using those two to create the two factors. So I would need to put in here, what? Minus here and minus here. And then if I distribute this through here and here, it turns it into what I had up there before. X minus a half minus root 31 over 2I. Then this one would be x minus a half plus root 31 over 2I equals 0.
Difference of squares or something?
No.
It just said it changes to trinomial.
It's okay, yes, but that's because it looks weird because there's 3 terms, but this right here is a complex number. These two together is a complex number. We're used to seeing x minus, what, a nice real number? We're not used to seeing 2 pieces there, but that's what a complex number is. Okay, let's see if we can somehow from this, well, there's one more thing I have to throw in here. There is a fundamental theorem of algebra, all right? There's also a fundamental theorem of calculus. So a lot of times in my calculus classes, when I show them the fundamental theorem of calculus, which happens right at the end of Cal 1, I ask them, do you remember there was a fundamental theorem of algebra? And usually people don't remember it. But it is what it says, fundamental. This is one of the major results of algebra, and that is, now there's different versions of it. There's different things I can stress. Here, the version I'm going to give you is all you need to know about it, all right? So if f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 1x plus a sub 0. What is that? We studied this a while back. What kind of function is this? Polynomial. Remember how we graphed polynomials? Bounce, touch, right? Okay? Yes? So this is a polynomial function. The fundamental theorem of algebra says that if we have a polynomial function, then there are exactly n factors. Some may repeat. What we're saying here is that if I give you a polynomial function and it has the highest power you see is n, I guarantee you it factors into n different factors. Some of them might be the same factors, but you're guaranteed n of them. All right? Which means that you should have n of these, right? Some of them might have complex numbers in them, but you're guaranteed n. So here, this was a third-degree polynomial. We have 3 factors. None of them were complex, though, right? They're all nice numbers. This says we're guaranteed to have all n. They've got to be there. Then after this theorem, we have something else that's going to be very important for you being able to do what we're about to do and what's going to be on the test. We're almost to what's going to be on the test. This is called the conjugate pair. Is it called a theorem? Yes. The conjugate pair theorem says this. If the book uses R, I'm going to use X. If X equals A plus BI is a 0 of a polynomial, so if you have a 0 of a polynomial that turns out to be a complex number, all right? If you have a 0 that turns out to be complex, we just had that a second ago, didn't we? We had 3i, right? And negative 3i. Those were zeros of this polynomial. If a plus bi is a 0 of the polynomial function, so is x equals a minus bi. Minus instead of plus. Now look at the name of this theorem, conjugate pair theorem. It means that what this theorem is saying is that if you have a complex number that gives you a 0 of the function, its conjugate pair has to also be a 0. So if a plus bi works, a minus bi will also work. Just a second ago, we had a problem where 3i worked, right? What else worked? Negative 3i. That wasn't just by chance. This theorem guaranteed that was going to happen. You could not have 3i and 4i, just those two. Because if you have 3i, negative 3i has to be there also. If you have 4i, negative 4i has to be there also. So they come in pairs. All zeros, all complex zeros of a polynomial function come in pairs. Now, let's go. Let's do it. It's time to see what we're going to need to do on the test. Yes. Pardon? The test is next Thursday, week from today. All right. Solve x cubed plus 3x squared plus 25x plus 75 equals 0 if negative 5i is a 0. All right, you ready? No? Be honest, yeah. All right, so if we want to solve this equation, let's just start from scratch. If I asked you to solve this equation, how would you try and solve this? You want to try grouping first? See if it works? Okay, x cubed plus 3x squared plus 25x. I'm seeing a lot of you on your phones today, and I know that we're all friendly and happy with each other, but I have a policy about phones. 10 points off your next test. I just don't want it to get to the point where we're all so comfortable with each other you're not even paying attention to the rules anymore. Okay? I don't want to have to enforce that, but I will. What? I'm just giving you a fair warning. All right. All right, so grouping, I take the first two terms, I pull out a GCF. So what can I pull out here? X squared. I'm left with x plus 3, right? What about on the other one? Can I pull something out? 25, and I'm left with x plus 3, and that's great, isn't it? That works great for me because I can pull out the x plus 3. I'm left with x squared plus 25 equals 0. Now, let's see if anyone can figure out what the next step is. You don't have to do much work. Let's see if you can set them both equal to 0. Yes, you can. But what can you tell me about this piece right here? I want you to go back and use this right here. We know that that's a 0, right? Which means what else is a 0? Plus 5i. And if we have the answers, we can go back to the factors, can't we? So this is a quadratic. I know that this should factor to be two things, yes? One of them I'm going to get from this answer. I go back and I take the opposite of that and put it next to an x. So this should be x, what? Plus 5i. And then what's the other one? Because the conjugate pair, positive 5i has to also be a 0, according to the conjugate pair theorem, which means, I'll put it up here, this means 5i also a 0. Right? Which means I put what down here? X minus 5i. Now it's completely factored, isn't it? And now you set each of these factors equal to 0. What are our answers? From here, negative 3. From here, negative 5i. From here, 5i. Those are your three answers. Yes.
Is that what you're gonna do? That's factors.
I'm going to ask you to solve the equations, including your complex number answers. Completely solve all possible solutions.
Can you give us imaginary?
Well, not on this one I did, just to kind of get us going. On some of them I won't. Yeah. We'll do one of those in a second. Let me do another example. Any questions, though? Yes? That one worked out good because grouping worked, right? That's it. Give me the solutions. Now, also, fundamental theorem of algebra. How many factors should we have had? 3, right? And we had 3 solutions. Now, you could have repeated factors. You could have had like x plus 3 squared, which would have been a repeated factor.
What? We're guaranteed 3 factors because why?
The fundamental theorem of algebra. 3, the power up there is 3. Guaranteed 3 factors.
If not more.
Not more than 3. That's what the fundamental theorem says. You're going to have 3 factors at the most. So you can't have a third degree polynomial with 7 factors. It's impossible. All right, let's try another one. So I want us to solve this equation. X to the 4th minus 7x cubed plus 14x squared minus 38x minus 60. And I'm going to give you that x equals 1 plus 3I is a 0. I forgot to put equals 0 at the end of that. Okay, how many factors should we have? 4. We should have 4 factors. I'm given one of the zeros, right? What can I also say is another 0 of this problem? So x equals what? The conjugate pair, 1 minus 3i. Notice that the 1 doesn't change, right? The 1 doesn't change, it's just the sign here changes. That's the conjugate pair. So I did it in red because that wasn't given to me. I had to kind of pull that out of the theorem. Is also a 0, right? You know what? Okay. Any ideas? Synthetic division again? Numbers inside the box? 1. Okay, you're giving me the list. Sorry, I'm here. Yep. Okay, so my list, you could make the list. We're going to start with 1, right? 1, then negative 1. See if 1 works. 1. Somebody else start at like 2, and because I haven't done this problem. Someone else start at 3, and just see if anyone can. First one to get it, let me know. What's that? 8. Oh wait. Oh man, close. Okay, 1 didn't work. 2? What? No. Negative 1 works? Where? Oh, 22. Yes. 22. Good. So that gives us negative 60. 60. Yes. Yes. All right. So that means that I can rewrite this polynomial up on top as what? X plus 1, then x cubed minus 8, x squared plus 22, x minus 60, right? That's the original one. And now I must go Again with synthetic, right? Try and break this down, unless grouping works, but I don't think grouping is going to work. You following me? What I want to do is I want to take it down all the way to where it becomes a quadratic. Why do I want to stop when it becomes a quadratic? These two are zeros, right? So from those two, I'll be able to recreate two factors. Yes? And those two factors will account for the quadratic. All I'm missing is one more factor. Do y'all see that? One more factor is the only thing I don't have. So another synthetic. Has anyone tried something else that works?
So then, like the quadratic should end up being 1 plus 3i and then 1 minus 3i because you would already have it minus 1.
Yes, that's right. Yes. Well, it's not going to turn out to be. It's going to be x minus one of those and then x minus the other. But here, let me ask you this: if this is one of my factors, right? And those two right there are going to create two other factors, then I can only have how many more? One. So is it possible for it to be a complex factor? They have to come in pairs. So it couldn't be. So it's got to be a real factor. All right, so let's, anyone get it yet? No? It's not going? Okay, let me help out, all right? What was the thing we were trying to factor or to solve? The one that had the after this first synthetic division, it was x cubed minus 60. Okay, 6 will work. 6 works. Now look on your test that I've already told you I'm going to make it so it happens within the first few, okay? But I pulled this one out of the book. The next one that's going to happen is 6. 6, and I'm going into 1, -8, 22, and -60. So 1, let's see, 6, -2, -12. Whoa, is that right? Yeah, 10, 60. So now here's where we are. We have x plus 1. This comes down, gives me what? X minus 6. And then the remaining thing in there is x squared minus 2x plus 10. Y'all okay with that? Sure? Yeah. This right here, since it's quadratic, I know it comes from two factors, but I have not used the complex factors yet, the zeros. So what I'm going to do now is I'm going to say this is x plus 1, x minus 6. These two break down to be, all right, xx. And then you could put minus, and then just put in your two complex factors. What are they? What were they? 1 plus 3i, 1 minus 3i. I'm going to stick those in there. 1 plus 3i, 1 minus 3i. We would just have used quadratic formula on this. Okay. Nope, same thing here. It's always the opposite, right? From 5, I go back to negative. Negative, negative, yes. All right, now I want to set that equal to 0. Give me the answers. What are my solutions? From here, -1. From here, 6. From here, you're going to have both of these. 1 plus 3i, 1 minus 3i. Those are your 4 solutions. Now, be careful. X-intercepts, we have to be careful now because these are our 4 solutions to the equation. But if you were to graph this, these would not be x-intercepts because our graphs only live when we're talking about real numbers. No, you could graph this, but remember what we did last time, and this was in one of your take-home problems, is that if this has imaginary answers, then there is no x-intercept. See, these aren't x-intercepts because they live in 2-dimensional space. It's not. Again, we're kind of getting into this point. It's like, well, why are we showing you this now when you're not even allowed to deal with them? When you graph stuff, you're not allowed to use imaginary numbers. So I have a hard time swallowing this pill of having to show you this. I think it's too early. All right. Let me just show you why it's too early. All right? Just to try and convince you of why it's too early. No, I'll convince you. I want us to go back and just look at a function we should all know. F of x equals x squared. Right? I'm going to show you something to look at it in a way that you haven't really looked at it before. Your domain. You're allowed to plug things in, right? To this function, and it spits things out. I'm going to put its range over here. Those are things that come out. So what would happen if I take the number 0, plug it into this function? So I'm going to go pick up the number 0 out of the domain. I'm going to plug it into the function. What would it spit out on the other side? 0. Now, let's pick the number 1. Let's plug the number 1 in and see what it spits out. What does it spit out over here? 1. Okay, now let's take the number 2. Plug 2 in. What does it spit out over there? 4. Right? If I take the number 3 over here, it'll spit out 9. This is a visual representation of what's happening, but that visual representation sucks. So what we do instead is this. We draw the domain here, which we call the x-axis, and we draw the range this way on the y-axis. So now when I say I'm going to plug in 0 for x, what do I get out? 0 for y. So it's here. If I plug in 1 for x, what comes out for y? 1, so I put it up 1, right? If I plug in 2 for x, what comes out? 4 for y, so it's here. And if I connect all those dots, I get the parabola, don't I? So when we look at functions in this class, when we've looked at them, the graph of it is a visual representation of both the number going in and the number coming out. We need the x-axis for our domain and the y-axis for our range. The x-axis for the input, the y-axis for the output. The x-axis is one-dimensional, the y-axis is one-dimensional. You put the two together, you have 2 dimensions. So why is it that we can't study complex numbers in a class like this? Well, what if I define a function, f of x, to be x squared, but now I allow you to plug in complex numbers? The domain can be complex numbers. So I have what? 2 dimensions, right? That's where you're going to grab your point from. And when you square it, it's going to spit something out, right? And it's going to spit out another complex number, isn't it? And I'm going to need to do it over here and spit it out. So if I take something like, I don't know, I, and I square it, where does it spit it out? What's I squared? -1? It spits it out there. Do y'all see that? And if I take another number, it's going to spit it out somewhere else, right? Now, that picture sucks. Let me try and put it together. What's wrong? Why can't I do that? Why can't I put them together into one nice picture like I did here? In order to draw this, I needed one axis to show my input, one axis to show my output. Here, I would need what? 2 dimensions to show my input, 2 dimensions to show my output, which is 4 dimensions. We live in three-dimensional physical space. How am I going to visualize four-dimensional space? Not easy to do, right? Do you understand that? So why then that becomes very challenging at this level to try and understand things that are happening four-dimensionally. So that's why we don't do it. That's why that exactly what does it look like? I can't draw it. Can't draw it. Calculator can't draw it either. We live in three-dimensional space. The fourth dimension, people say, is time. You can have time as this fourth variable. You know, like I'm standing right here. I haven't moved, but what's changed is time. So there's that fourth thing. So we're limited, okay, on how far we can take our mathematics by what we're comfortable with, and a lot of what we're comfortable with is because we see and we feel, and we live in three space. There are a lot of very brilliant mathematicians who are blind, and a lot of them are very good at this because they're not stuck in physical space the way we are. They're not fixated on needing to see it the same way we see it. So in math classes, what we would say is this is a function right here that goes from two-dimensional space into two-dimensional space. From two space to two space, you need four dimensions to see it. And then as you go on and do more and more and more and more math, there's no restriction on how big these spaces can be. You can go from 3 space into 5 space, or you can go into 10 space into 20 space. It doesn't matter. And then all visuals are gone. So that's why we wait to really treat complex numbers properly till after you've taken Cal 1, Cal 2, Cal 3, linear algebra. Those 4 classes out of the way, then you can start to maybe see this stuff and be able to handle it, because it's so hard to draw it. No. That's why I think it's kind of a travesty that we sit here and we just barely open the window on imaginary numbers, but really we cannot seriously treat them. We can't. We can't seriously look at complex numbers in a class like this. Can't do it. All right. I apologize. It's part of the curriculum. I have to do it. So I've been arguing. No one wants to listen to me when it comes to, whether or not we should talk about complex numbers. Okay, last example, and we're going to call it a day. This is 5-6. 5-5 we did. It's synthetic division. Yeah. Yeah, it's called something else. Real zero is a polynomial function. They're showing you another way to get your zeros using synthetic division. Yep. X cubed. Well, you know what? Let's go with the harder one. Well, that way you have an example that's somewhat challenging. Now, I think what I'll do is I'll walk you through this one. 38 from 5, 6. There's an app for that. Oh, yeah. Just go to Wolfram Alpha and type this in, and it'll do everything for you. It'll factor it alpha. Well, you know this program that I've been using throughout the semester? This program is made by Wolfram, a company called Wolfram. This is called Mathematica. Wolfram Alpha, the brains of that website, is the kernel of this program. So, yeah. Wolfram Alpha is far and away the way to go. Okay, so what I would like for us to do is I'd like for us to find all the zeros of this function. All the zeros, including the complex zeros. So I'm going to guide you through this because time issues, right? I'm going to guide you. Where is it? This is 36. Hold on a second. Yeah, I'm ending with the crap one, right? I'm sorry? Well, no, no. Let's look at this for a second. All right. This is not quite what I was hoping it would be, but how many distinct linear factors should we have? Or how many linear factors should we have? We should have 4, right? Because it's fourth degree polynomial. I'm not giving you any information about any zeros, right? I'm not giving you anything. So you could have all real zeros, like this one. You could have all real zeros. If you had a complex zero, they would come in pairs. So you could have 2 complex zeros and then 2 real ones, right? Or you could have 4 complex zeros and no real ones. Do you follow? And this one has 4 complex zeros, but there's no way you would really know that. And if there's 4 complex zeros, then you're never going to be able to get a real zero, which means that if you do synthetic division using this crappy number 252, every single number you use is not going to work. That would not work. Okay? Hmm? That's right. But how do you get them? That's the big question. How do you see? It's not a quadratic. So what do you do, right? So I think because this is beyond what I would ask you on the test, I think what I'll do is I'll just add in one more piece of information for you. X equals 2I is a 0. Next class, we'll come back after you've gone home and looked at the review. I'll come back and I'll address this question. We'll do it without that information. I'll show you how it's done. All right? But for now, let's just continue with this idea of me giving you a little piece of information, seeing if you can get the rest. So what does that tell you? If 2I is a 0, then what else is a 0? No, negative 2I is a 0. But if you go through the synthetic division, nothing's going to happen with the 252. Do y'all agree? So here's what watch the way I do this. Here's what I know so far. This thing factors. I know that it's going to give me an x minus 2I and an x plus 2I. Do you agree? Right? What I don't know is this part right here. So I'm going to do something that we haven't done, and this is because you need to see it. Multiply these two together. FOIL them real quick. What's x times x? Okay, what's x times 2I? x2I. What's negative 2I times x? Negative x2I. And what happens to those two? They cancel. And then what's the last one? So we got x squared was here. We got negative 4I squared, which is going to turn into positive 4, because the I squared is negative 1. So this is really x squared plus 4. Yes? That times something is my original function, isn't it? I just don't know what that thing is. So that times something is my original function. Let me write the original function down here. I'm trying to see if I write this down, if someone can tell me what we can do. Hold on. Sorry. Okay, so let me backtrack. Here's the original polynomial. I'm trying to break it up, right? Trying to factor it. I gave you this information which told you this was true also. These two pieces of information told you that these were factors. Multiplying these two factors together gave us x squared plus 4. We know that the original function breaks down to be x squared plus 4 times something. So what is the something? How do we figure out this something? Anyone see what we can do? If I want to know what this is, get rid of this on this side. Long division. We're going to take this and divide it through on both sides. And this divided by this is that, isn't it? So you'll have to do long division. This divided by this. So I'll leave it like this. The question mark is equal to x to the fourth plus 3x cubed minus 19x squared plus 27x minus 252 all over x squared plus 4. Now, I'm going to leave that to you as an exercise to do on your own. You remember how to do long division? It's part of what you need to review for the test. So do that on your own. What you should get when you're done here is x squared plus 9. Right? So this long division done somewhere else should give you this answer. So the remainder will be 0. So the original problem up here, all right? The original problem is x squared plus 9, x squared plus 4. And I'm hoping that from that you can say exactly what you just said, that everyone can see that that now can give you your 4 factors pretty easily. Because where did x squared plus 4 come from? X plus 2i, x minus 2i? And where do you think x squared plus 9 is going to come from? X plus 3i, x minus 3i. Do what? Because it's a plus here. If that were a minus, mm-hmm. Yes. Well, yeah. If you set this to 0, right? But I wasn't really using that logic. I was using the logic of this. We had started with this, right? And then we multiplied those two together, and we were able to determine that it turned out to be this. I was trying to get you to see that, look, working backwards from here to here, like going reverse, if we see x squared plus 4, it's x plus 2i, x minus 2i. So if that was an x squared plus 9, that'd be x minus 3i, x. But you could also just move it over and do square root. From the long division. Long division gave us this. Okay, so at the end of the day, we have 4 answers, right? We have 4 zeros. Is that what I wanted? No, if you were to graph this polynomial function, look at this. If you were to graph this polynomial function, it would not touch the x-axis anywhere, which means it would always be above or always below the x-axis. And I can tell you right now it would be above. The reason I know that is because it's a fourth degree polynomial. Leading coefficient's positive, both ends go up. If both ends go up, there's no way it can cross the x-axis. It has to be above the x-axis. Okay, look, the review for the test. Let me just give you a snapshot of it. Where is it? I haven't posted it yet. I'm going to post it tomorrow. Just to give you an idea of the things that we're going to be looking at. Okay, sketch the following polynomial functions. These should be very quick sketches because you already know the x-intercepts. You just have to figure out bouncing and touching and left and right behavior, and you're done. This one, I give you a polynomial function, and it has certain x-intercepts. It bounces at certain places. It crosses at others. It has a y-intercept. You're supposed to construct a polynomial function from that, which might look like that. They can all vary a little bit. Okay, and then this one is very much like this, except there's no picture. It's just, it has these zeros. It's a degree 3 polynomial. And it has a point in it. There was a problem just like this I gave you. A lot of this, I just went right to the notes or to the quiz and just took those problems and tweaked them. Sketch this polynomial function. That's the one where you have to follow the steps from class. Rational functions. Oh man, where's the division sign? I don't know where the division bar is on this one. But I gave you 3. Why do you think I gave you 3 rationals? Not because I'm going to give you 3 on the test. Remember for the horizontal asymptote, there were 3 cases? So I gave you one of each case. Just so you could practice. Yes? I'm going to give you the cases. What I want you to do is try and do as much studying as you possibly can without relying too much on the steps and everything, the table. See how comfortable you are without all of that. We're going to have to kind of see. I've been getting a lot of pushback from faculty to not give cheat sheets and all this stuff, but just practice. I mean, the 3 cases, you know, it's just 3. Okay, let's talk about it Tuesday. Solve this inequality. That's from last class, right? It's a polynomial inequality. Solve this inequality. That's a rational inequality. So those 2 are from last class. Find all the solutions, including complex, for this. Find all the solutions for this. This is today, all right? Given that 4i is a solution to this equation, find all the solutions. That's from today. So I think everything on there is doable. My only hint on 10 and 11 would be that on 10 and 11, you start with synthetic division. Those are going to work out nice, not like that last one I just showed you. All right, so that gives you kind of an idea of what the test will be like. Please look at that over the weekend. Come back on Tuesday and start addressing questions. We're not going to cover anything new on Tuesday. So come with questions. Strictly review. Yep. Okay. I'm going to post this probably today. I didn't know if I would have it done in time or what we would cover today, but I think we're okay with this now. I hope.
So I wasn't able to check if the attendance
Last name. Okay, got you. Same thing. What was your last name? Where are you? R.A.? Where the heck are you? Did you register late or something? Or this is an old roster? Okay. You're still showing up on the class though, right? Like in Canvas? All right. I'll put you down in here. That quiz that I said. Okay, thank you. I have not touched those yet. No, I'm a little backed up.
No, that's okay. I assume you try to see what comes up.
Yeah, um, I have not, and I probably won't get to them until next week.
That's
Yeah, I've got this is a busy time of the semester for me because I've got midterms,
right.
even my internet classes, and so I've got a lot of stuff going on. But I'll get caught up. Most likely by the time you take your test, when I give you that test back, because I usually grade those like you'll have the next class. At that point, you'll know exactly where you are.
Okay.
Like all grades will be in. Okay?
And are you gonna? You said you were
Am I
gonna
still
drop the grade.
recording?
Are you gonna do that before?
I